Hello dear, welcome to my YouTube channel Innovative Creator. Subscribe for more innovative videos. Let's start. Following the same legacy, the designers at Northrop partnered with McDonnell Douglas to design the F-23, which many still consider to be the most technologically advanced aircraft than its competitor. The F-23 prototypes were 67 feet 5 inches in length and had a wingspan of 43 feet 7 inches, slightly bigger than its competitor, the F-22, giving the F-23 a slight advantage in range and speed. The prototype air vehicles PAV-1 and PAV-2 were powered by two Pratt & Whitney YF-119 and two General Electric YF-120 afterburning turbofan engines, respectively. Both engine types were able to meet the minimum ATF program requirements of generating 0.00 pounds of thrust with afterburner, with the ability to supercruise. However, in the end, the Pratt & Whitney YF-119 was chosen to power the winning entry of Lockheed's YF-22. Both prototypes could reach a maximum speed of Mach 2.2 and supercruise at Mach 1.6. Northrop's prototype was the first to take to the skies, with PAV-1 taking its first 50-minute maiden flight on the 27th of August, piloted by Alfred Paul Metz. PAV-2 took flight shortly after on the 26th of October, piloted by Jim Sandberg. By all accounts, the design of the YF-23 was brilliant, with some very advanced design elements. The aircraft was configured with diamond-shaped wings or trapezoidal wings, allowing the designers to reduce aerodynamic drag at transonic speeds between Mach 0.75 and Mach 1.2. This meant that the aircraft had good low-speed performance despite being an overall fast jet. The trapezoidal wing setup also offered advantages for high-speed flight, with a small and highly loaded wing substantially reducing drag at supersonic speeds. The wing's tapered layout also reduced structural stresses, allowing the wing to be made thin and using less material during construction, keeping the overall weight of the aircraft low. Along with the unusually shaped wing, the YF-23 also featured an all-moving V-tail in favor of the more traditional vertical fins and horizontal surfaces. This kind of tail design, sometimes called a butterfly tail, is unconventional but offers advantages such as reducing the overall exposed surface area of the tail, leading to less parasitic drag and making the rudder controls more effective, allowing the pilot of the YF-23 to achieve more airspeed and maintain proper controls during high-speed flight. Moving forward, the cockpit of the YF-23 was placed very near to the nose of the aircraft to improve overall pilot visibility. The aircraft had a conventional tricycle undercarriage layout, with the internal weapons bay placed on the underside of the fuselage between the nose and the main landing gears. This meant that the aircraft would carry all its weapons inside and not on wing hardpoints, maintaining all aspect stealth, as weapons on external hardpoints are the primary factor in increasing an aircraft's radar cross-section. The two engine manufacturers powering YF-23's PAV-1 and PAV-2 were in their own competition to produce the best-in-class supercruise-capable engine. Combined, both engines on YF-23 produced approximately 70,000 pounds of thrust, equivalent to more than 40,000 horsepower. In comparison, an average Arleigh Burke-class destroyer has a total of 100,000 shaft horsepower. This new generation of engines almost doubled the thrust available to the YF-23 from its nearest counterpart in the U.S. Air Force service, the F-15 Eagle, whose two Pratt & Whitney F-100 engines could only produce around 40,000 pounds of thrust in the afterburner setting. This increase in engine performance was a big technological breakthrough for the ATF program, leading to the creation of the first supercruising jet fighters in the world. It meant that fighter jets would no longer have to rely on gas-guzzling afterburners to reach supersonic speeds, saving valuable fuel and increasing the overall range of the aircraft. A major challenge for ATF program designers was to provide stable airflow to high-performance engines on an airframe that's hard to spot on radar. The issue had to do with airflow boundary layer, which is air that spreads around the aircraft's fuselage as it flies. Boundary layer air can flow at different velocities and directions compared to the air that's offset from the aircraft's surface, leading to large drops in engine efficiency during certain regimes of flight. Boundary layer air can become highly turbulent, impacting the engine's performance or even suffocating it at supersonic speeds. The YF-R-23 featured a trapezoidal engine inlet with S-ducts and a clever solution to manage this issue. Prior to the ATF program, supersonic jets dealt with this problem using elaborate splitter plates to separate the two airflow streams and maintain uniform supply through the inlet opening. But those concepts were not conducive to stealth, as even a small gap between the inlet and the fuselage could result in a radar cross-section increase. The designers of the YF-23 came up with an innovative solution, installing gauzing panels ahead of where the fuselage meets the leading edge of the air inlet. These panels had small holes drilled all over them and would suck up the boundary layer air sticking to the fuselage before it entered the air inlet. This air was then vented out through a pair of small doors on the YF-23's upper surface, acting like an invisible splitter plate. The system, called the Boundary Layer Control System, worked automatically, feeding the massive engine compressors with a steady stream of air even at supersonic speeds while maintaining all aspect stealth. Unlike its competitor, the YF-23 did not feature a thrust vectoring engine nozzle, which some consider a disadvantage for maneuverability. However, according to the designers of the aircraft, they sacrificed a little bit of agility to gain a lot more survivability. Due to the flat nature of the YF-23's fixed-engine nozzles, the designers were able to line them with heat-ablating tiles, reducing the infrared signature, IR signature, of the aircraft to heat-seeking surface-to-air and air-to-air missiles. This was a crucial aspect, as IR signature reduction is essential for stealth aircraft, making them less susceptible to infrared-guided missile attacks. The main weapon system that an enemy will deploy against a low-observable stealth air superiority fighter, like the YF-23, is a heat-seeking missile. Just like the company's B-2 bomber, the heat-ablating tile significantly dissipated the engine nozzle temperature, which ranged between 3,000 and 4,000 degrees Fahrenheit. In order to be maneuverable and maintain its agility during air-to-air combat, the YF-23 prototypes were installed with multiple aerodynamic instabilities, all controlled by its advanced fly-by-wire system. The YF-23's core processor was considered the most advanced supercomputer of its era, performing nearly 5 to 6 billion operations per second. The system not only managed the flight controls of the aircraft, but also provided radar, navigation, performance data, and situational awareness to the pilot in real time. The armament system of the YF-23 prototypes was based mostly around air-to-air missiles and air-to-ground bombs. Since all missiles and bombs had to be carried inside the internal weapons bay to maintain stealth, the overall payload capacity was not as great compared to other conventional fighters. Despite this, all the necessary weapons needed in an air superiority fighter were available to the YF-23's pilot. The aircraft could carry the standard AIM-E9 Sidewinder for close air-to-air fire, and also the AIM-120 AMRAAM or the AIM-7 Sparrow for medium to beyond visual range targets. The aircraft also featured a main M61 Vulcan cannon, which could fire 20mm rounds at a very high rate of fire, around 6,000 rounds per minute. Given the mission types, it also had the capability to carry up to two 1,000-pound or 500-pound air-to-ground bombs. In conclusion, the two YF-23 prototypes tested well and checked all the boxes required for the ATF program, and some argue it even beat its competitor, the YF-22, in areas of speed, range, and overall performance. However, after 4 grueling years of testing and evaluations, the YF-22 was selected as the winner over the YF-23. The designers of the two YF-23 prototypes have always remained firm in their belief that their aircraft was superior and more technologically advanced than the YF-22. However, various political forces and lobbying swayed the decision in favor of Lockheed's YF-22, which is still currently in service as the F-22 Raptor. A total of 195 F-22 Raptors were produced, and production finally stopped in 2011. On the other hand, the two YF-23 prototypes, PAVs-1 and PAVs-2, were donated to air museums and are never to be flown again. In recent years, there has been a glimmer of hope for the revival of the YF-23 in the form of Japan's F-3 sixth-generation fighter. Japan is seeking the help of Northrop Grumman in aiding their design and development of its F-3 fighter program, and given the entire experience gained during the development of the YF-23, The company is optimistic about securing the contract for this project. Regardless of what is in store for the future, as aviation enthusiasts, we would love to see the return of the F-23 in its reincarnated form, taking to the skies and finally bearing fruit to all the research and hard work that was spent on making this magnificent aircraft that everyone seems to have forgotten. So, what do you think about the possible